Welcome back. In the last lecture we discussed vapor absorption refrigerant systems based on water lithium bromide pair. In this lecture I shall introduce systems based on ammonia water pair. Okay, so the specific objectives of this particular lesson are to discuss differences between water lithium bromide and ammonia water systems, and discuss properties of binary mixers with reference to composition, vapor pressure, enthalpies of liquid and vapor mixers, and finally discuss some basic steady flow processes using binary mixers. At the end of this lesson you should be able to explain basic differences between water lithium bromide and ammonia water systems, explain the need for rectification in ammonia water systems, evaluate properties of ammonia water mixers using charts and equations, and analyze basic steady flow processes involving ammonia water mixers. Let me give a brief introduction. As the name implies, absorption refrigerant systems using ammonia water. Ammonia is a refrigerant and water is the absorbent, and they are extensively used in refrigeration applications. Since ammonia is a refrigerant, it is possible to provide refrigeration at sub-zero as well as above 0 degree centigrade temperatures. That means actually ammonia water systems are much more versatile than water lithium bromide systems, because you do not have the problem of temperature restriction, whereas in water lithium bromide systems you cannot operate the system below 0 degree centigrade, whereas ammonia water systems can be used for both sub-zero as well as above 0 degree centigrade application. That means you can use them for air conditioning as well as refrigeration applications such as cold storage. Okay, so in this manner they are more versatile. However, compared to water lithium bromide systems, the analysis of ammonia water systems is relatively complicated. In fact, I have mentioned this in the last class. The complication comes because the vapor generated in the generator is a mixture of refrigerant and absorbent. And what is the reason for this? The reason for this is the low boiling point temperature difference between ammonia and water. This is about 133 degrees centigrade. In water lithium bromide systems, the boiling point temperature difference between the absorbent and refrigerant is very high. As a result, in the generator, as I mentioned in the last class, you will not find any absorbent, or the amount of absorbent is practically negligible. That means what you have in the generator exit is a pure water vapor. Okay, so in the refrigerant circuit you have pure refrigerant circulating, whereas in the ammonia water systems, because of the low boiling point temperature difference, when you boil the solution you find that both ammonia vapor as well as water vapor both are generated in the generator. Okay, so if nothing is done, then both refrigerant as well as absorbent enters into the refrigeration circuit, and this will create some problems which I will show now. So, if water is allowed to circulate with ammonia in the refrigeration circuit, what are the problems? The problems are, first problem is that the heat transfer in condenser and evaporator becomes non-isothermal, then evaporator temperature increases, evaporation will not be complete, water may get accumulated in the evaporator leading to malfunctioning of the plant, and finally the circulation ratio also increases. All these effects are detrimental to system performance. So, what we have to do is we have to minimize the concentration of water vapor in ammonia at the exit of the condenser or at the inlet to the at the exit of the generator or at the inlet to the condenser. We have to ensure that almost pure ammonia vapor goes to the condenser. So, this requires additional components, namely a rectification column and a deflegmator. As a result of this, you will find that the design of ammonia water systems are more complicated, and the cost also is higher because of the additional components. Not only that, due to these additional components, the system COP is also reduced when you compare it with water lithium bromide system. So, these are the main differences between water lithium bromide systems and ammonia water systems. Now, let us first begin the discussion with properties of ammonia water solutions. As we have done in the last class, let us begin with composition. So, similar to water lithium bromide solution, we can also define composition of ammonia water solution in terms of either mass fraction or mole fraction. However, there is one important difference. In case of water lithium bromide systems, the mass fraction, mole fraction, composition, everything is defined in terms of the mass or number of moles of lithium bromide. That means it is defined on the basis of the absorbent, whereas in case of water ammonia water systems, the mass fraction and mole fraction are defined on the basis of ammonia, that means they are on the basis of refrigerant. Okay, so as a result of which the meaning of strong and weak solutions will be different for these two systems. Okay, I shall discuss this in the subsequently, but you have to keep in mind that when I say mass fraction in water lithium bromide system, it means mass of the lithium bromide to the mass of the total solution, whereas in ammonia water systems when you say mass fraction or mole fraction, that means we are always referring to the mass of the ammonia or number of moles of ammonia in total in the total mass of the solution or in the total number of the molecules in the solution. Okay. So, the mass fraction is defined as mass of ammonia Ma divided by the total mass of the solution, that is Ma plus Mw, where Ma and Mw are masses of ammonia and water respectively. Similarly, just like the earlier this thing, the composition can also be expressed in mole fraction. So, if I am writing this in mole fraction, this is the liquid phase mole fraction. X is defined as the number of moles of ammonia in liquid phase divided by the total number of moles in liquid phase. Okay, and this can be easily obtained from the mass of the substance and its molecular weight. For example, Na, that is the number of moles of ammonia, is equal to mass of ammonia divided by the molecular weight of ammonia. Similarly, the number of moles of water is equal to mass of water divided by the molecular weight of the water. And for calculation purposes, you can take the molecular weight of ammonia as 17 kg per kilomole and molecular weight of water as 18 kg per kilomole. However, there is one important difference between lithium bromide water lithium bromide systems and ammonia water systems. Because the vapor above ammonia water above the solution consists of both ammonia vapor as well as water vapor. Okay, that means we have to talk about composition in the liquid phase as well as composition in vapor phase, because you have mixer in both liquid as well as in vapor phases. Okay. So, to distinguish between the concentration in liquid and vapor phases, we define superscript L for liquid phase composition and superscript V for vapor phase composition. So, when I say XL, that means mole fraction in liquid phase. Similarly, X superscript V means mole fraction in vapor phase. Okay, this is the nomenclature I will be using throughout this lecture. All right. So, similarly, zeta L stands for liquid phase mass fraction and zeta V stands for vapor phase mass fraction. Vapor phase composition can be found by assuming ideal solution behavior. If you are assuming that it is behaving as an ideal solution, then you can apply ideal gas equations like Dalton's law, etc., and you can find out the vapor phase composition. But the actual mixer deviates from ideal behavior. So, the actual composition have to be obtained from equilibrium vapor pressure composition charts or equations. Okay, so, let me just show a typical vapor pressure composition chart. Okay, so what I am showing here is a typical vapor liquid equilibrium chart, where you have mass fraction of ammonia in vapor phase as x axis and y axis is pressure or saturated temperature of ammonia. Okay. So, this is an equilibrium chart, that means the vapor is in equilibrium with the solution. Okay. And also shown here are different concentration lines for liquid. Okay. These are the liquid constant liquid concentration lines, all these. Okay. So, if you know the concentration of the liquid, for example, let us say that this is the concentration of the liquid and this is the pressure, then you can easily read what is the concentration of ammonia in vapor phase. Okay. Similarly, you can find out from the pressure and solution also. Okay. Such kind of charts are available in literature, using which you can find out the exact composition in vapor phase from the knowledge of liquid phase composition and the pressure. Now, let us look at vapor pressure of ammonia water solutions. So, both ammonia and water vapor contribute to total pressure. So, we have to write from Raoult's law the total pressure. If you are assuming that the mixer behaves as an ideal mixer, then you can use the Raoult's law, and from Raoult's law you know that the total pressure P is equal to x into Pa plus Pw into 1 minus x, where x is the liquid phase mole fraction of ammonia and Pa and Pw are the saturated pressures of ammonia and water at that particular temperature. But we know that the ammonia water mixer deviates strongly from Raoult's law in a negative manner. So, you cannot really use the above expression when the concentration is high. Okay. So, let me give an example. At 40% mass fraction at 40 degree centigrade, if you are using Raoult's law, you will find that the total pressure is 6.47 bars. Okay. So, this is what is obtained from Raoult's law, but you will find that from actual measurements the total pressure is 3.03 bar. Okay. So, the deviation is really strong. This gives an activity coefficient of less than 0.5. Okay. So, vapor pressure data for ammonia water solutions are also available in the form of empirical equations and charts such as During plot and all, and I have discussed these During plots etc. in the last lecture, and the construction wise the plots will be exactly similar. That means the During plot for ammonia water system will be almost similar to During plots of water lithium bromide systems. Okay. Now, let us introduce an important concept of what is known as bubble point and dew points for ammonia water mixer. In fact, this discussion holds good for any binary mixer which is a geotropic mixer. Okay. So, since the mixer of ammonia water behaves as a geotropic mixer except at the eutectic points, at a eutectic point it behaves as a geotropic mixer, but otherwise it behaves as a geotropic mixer. So, what is the meaning of the geotropic mixer behavior? It means that at a given pressure change of phase takes place over a gliding temperature. Had it been an azeotropic mixer or had it been a pure fluid, then you know that change of phase takes place at a constant temperature. But if the mixer behaves as a geotropic mixer, you will find that change of phase, for example boiling or condensation, you will find that at a given pressure boiling and or condensation take place over a gliding temperature, not at a constant temperature. This is the nature of geotropic mixers. Okay. If it is as I have already repeated, if it is a pure fluid or an azeotropic mixer, the phase change takes place at a constant temperature when the pressure is kept constant. Okay. So, in the two phase region the composition of liquid will be different from the composition of vapor. So, let me explain this. Let us do a small experiment. Let us assume that we have a cylinder. Okay. And the cylinder has a free floating piston and this is loaded by fixed weights. Okay. So, these are the weights, and initially this piston cylinder arrangement consists of subcooled liquid of ammonia water solution. Okay. So, initially we have subcooled liquid of ammonia water solution and we are exerting a constant pressure because it is a free floating piston and the weights are kept constant. So, the pressure exerted on the system remains constant throughout the process. Now, let us say that we start heating the system or we start heating the solution by supplying heat to the solution. Okay. Then what happens? You will find that since the initial condition is subcooled liquid, to start with nothing happens. Okay. But as the temperature increases slowly, you find that at a certain point the first vapor bubble forms. Okay. So, if the cylinder is a transparent cylinder, you will observe that the first vapor bubble forms at a particular temperature. Let me call it as T bubble. Okay. So, T bubble is the temperature at which the first vapor bubble forms at a constant pressure. Okay. So, if you heat the solution further, let us say that state 2. So, you continuously supply heat, you will find that temperature increases and along with the temperature more and more vapor formation takes place. That means more and more liquid is converted into vapor. So, you can see that there is a lot of vapor here. Okay. So, this process continues as long as liquid is present. Okay. So, at a particular point you will find that the last liquid droplet also evaporates. That means at a particular temperature, let me call it as T dew point. Okay. The last liquid droplet evaporates. Further heating will simply result in superheating of the vapor. Okay. So, here you have vapor, here you have as I said the subcooled liquid, and here you have a two phase mixer consisting of vapor and liquid. Okay. Now, so let us say that you are plotting this process. Let me say that we have taken a graph paper and I have on the x axis I have composition and on the y axis I am plotting temperature, and let us say that P is constant here. Let us say that this is the initial concentration, okay, and you are plotting this process on this chart. Then you find that as you start heating it, let us say that this is the initial some initial temperature, okay. So, as you start heating it, at some particular point the first vapor bubble forms, okay, and at some other temperature the last liquid bubble droplet evaporates. So, you get 2 points here. Further heating will result in continuous increase of temperature, okay. Now, let us say that I repeat this experiment with another concentration, okay. You find that exactly same process appears, but these 2 temperatures will be different. So, instead of having temperatures like this, you will have another 2 temperatures, okay. If you are starting this process at this initial concentration, then again you will find that you will have some other temperatures, okay. So, if you carry out this experiment for different concentrations, you will find different temperatures, okay, and if you join all these temperatures, you get what is known as a dew point and bubble point lines for this pressure, okay. So, let me show this dew point and bubble point lines, okay. So, what I am showing here is a plot obtained by taking concentration or mass fraction on x axis and the temperature on the y axis. As I said, we are keeping the pressure constant, and this data is obtained by varying the concentration from 0 to 1. What do you mean by 0? 0 means it is pure water, okay. 1 means it is pure ammonia, okay. So, if you are carrying out the experiment taking pure water in the piston cylinder arrangement, you will find that you have only one point at which phase change takes place, because obviously pure water is a pure fluid. So, phase change takes place at a constant temperature. Let us say that you have marked that point on this temperature axis like this, okay. Similarly, if you are conducting the experiment with pure ammonia, again you will find that the phase change takes place at a constant temperature, which is nothing but the boiling point or saturation temperature corresponding to this pressure, okay, at P. Similarly, this is the saturation temperature for water, okay, at this pressure, and the intermediate points, as I was mentioning, are the bubble points for different concentrations, but at the same pressure. Similarly, the points on this line are the dew points at different concentration and at the same pressure, okay. And this line, what is called as the bubble point line, is nothing but the loci of all the bubble points, okay. That means if you have joined all the bubble points starting with the saturated point for water and saturated point for ammonia, then you get a curve of this shape, okay. So, this is your bubble point line. Similarly, if you join all the dew points, you get a line called as dew point line, okay. So, you have ultimately you get a shape of this form, okay. So, you get a dew point line and a bubble point line, and what you have here below the bubble point line, you have a subcooled liquid, and above the dew point line you have a superheated vapor region, okay. And in between the dew point and bubble point line you have the two phase liquid plus vapor region, okay. So, this is the typical dew point bubble point line lines for a constant pressure, okay. That means at a single pressure, and the process of the heating is shown here. As I explained to you, we started with a subcooled liquid. So, point 1 lies in the subcooled region. So, we started heating it, that means the temperature started increasing, and this is the point at which the first vapor bubble appeared. So, that is why this is the temperature, bubble point temperature at this concentration zeta 1 and at this pressure P, okay. So, if you heat it further, you are in you have entered into the two phase region, okay. So, that means you have both liquid as well as vapor. If you continuously heat it, you arrive at a point at which the last liquid droplet evaporates, as I have already mentioned, okay. And this temperature where the last liquid droplet evaporates, as I told you, is nothing but the dew point, okay. So, you can read the dew point and bubble point from this chart. What is interesting is the two phase region. See, if we started with initial composition of zeta 1, okay, and so in the subcooled region the concentration is zeta 1, okay. So, what is the concentration of the first vapor bubble that is formed here? You can find that one by drawing a horizontal line like this, okay, and where this line intersects the dew point line, that will give you the concentration of the first vapor bubble that is formed. Because what happens is, let us say that you have taken a solution which consists of ammonia and water, ammonia has much lower boiling point compared to water. So, when you are heating that solution and when you are keeping the pressure constant, and if you have heated it sufficiently, you will find that ammonia liquid starts evaporating first. Why does it evaporate first? Because it has a lower boiling point. Okay. And later water starts evaporating. So, the first vapor bubble that has formed will be rich in ammonia and weak in water vapor. Okay. So, as you continuously heat it, you will find that progressively the vapor that is forming will be rich in water, will be stronger in water also. Okay. So, initial vapor to be formed will always be rich in the low boiling point substance. Okay. In this particular case, it happens to be the ammonia. Okay. So, that is what I am showing here. The first vapor bubble is quite rich in ammonia vapor, ammonia this thing. So, the concentration is given by zeta 1 V, V stands for vapor as I was explained. And if you look at the point 2 where you have liquid as well as vapor. So, what is the liquid phase concentration and what is the vapor phase concentration? Since both liquid and vapor are at thermal equilibrium, both will have same temperature. Okay. So, T2L for example will be equal to T2V. Okay. And what you have here, you have a mixture of saturated liquid and saturated vapor. Okay. So, the concentration can easily be obtained if you are drawing this temperature line, and where this line intersects the bubble point line, that will give you the concentration of liquid. Okay. And where this where this line constant temperature line intersects the dew point line, that will give you the vapor phase concentration. Okay. So, by using this you can find out easily what is the concentration at different phases. So, it is interesting to see that the concentration will be different in the two phase region. Okay. And once you come back to the superheated region, again you will find that because of the conservation of the mass, the concentration again remains same. Okay. So, this is how once you have the charts you can find out at any point, for example at some other point, what is the concentration of the liquid, what is the concentration of vapor. Okay. At some other point, what this is the concentration of the liquid, this is the concentration of the vapor. Okay. Of course, this experiment can also be carried out in a reverse manner. That means, initially you can take a superheated vapor and start cooling the vapor. Okay. So, you can proceed either in this manner or in this manner. Okay. Ultimately, you will get the same curve. And for the two phase region, just now I have explained, you can write the mass balance. So, the total mass is always conserved, total mass is nothing but M2L plus M2V, and you can also write a conservation equation for the ammonia mass. Okay. This is nothing but the total mass of ammonia in the mixture, that is nothing but ammonia in liquid phase plus ammonia in vapor phase. Okay. So, you can write these two equations from the mass balance. Okay. And from these two equations you can easily show that you can eliminate M1, and you can easily show that M2 liquid by M2 vapor is nothing but zeta 2 V minus zeta 1 divided by zeta 1 minus zeta 2 L. Okay. Or you can also write this in this form. Okay. This particular rule is called as mixing rule, or it sometimes it is also called as lever rule. What do you mean by lever rule? Lever rule means this point actually acts as a fulcrum. Okay. So, for example, we want to find out what is the mass of this thing. Okay. The total mass into this distance will always be equal to mass of vapor into this distance. Okay. So, when as this distance increases, you will find that this point moves closer to this dew point line, that means vapor concentration increases. Similarly, when this point moves this side, you will find that liquid concentration increases. Okay. So, that is what is shown in this equation. Of course, if you have carrying out this experiment at two different pressures, let us say, then you will get two different lines. Okay. This is for one pressure P2 and this is for another pressure P1, and P2 is greater than P1. So, the same thing can be repeated at different pressures. So, at different pressures you will get different lines like this. Okay. Right. So, this is a typical bubble and dew point chart for a binary mixer. Okay. So, now let us look at enthalpy of ammonia water mixers. First, let us look at liquid phase enthalpy. Since strong ammonia water solution deviates from ideal solution behavior, the liquid phase enthalpy has to be obtained by this equation, that is H is zeta HA plus 1 minus zeta HW plus delta H mix. Delta H mix is negative because the mixing process is an exothermic process, just like water lithium bromide system. And the specific enthalpy at any concentration and temperature can be calculated from the above expression, provided we know the heat of mixing. Heat of mixing is normally obtained from measurements. Now, enthalpy charts for solution are plotted as a field of isotherms against mass fraction. In fact, I will show you the typical enthalpy chart for ammonia water mixer in the next class. So, normally they are plotted against mass fraction for different isotherms. And since pressure does not have a significant effect on liquid enthalpy except at critical point, normally the pressure lines are not shown on typical solution enthalpy charts. Okay, that means in the for the liquid enthalpy only the temperatures and concentrations are given. Okay, pressures are not normally shown. And it is also generally assumed that enthalpy of subcooled liquid is equal to the saturated enthalpy at that temperature. Okay, if you are assuming this, it will considerably simplify the calculation procedure, and it does not give really a big error. Okay, so it is a standard procedure. Now, enthalpy of liquid phase is relatively easy. So, how do we calculate the enthalpy of vapor phase? The complication comes because in the vapor phase we have both ammonia as well as water vapor. Okay. So, and the vapor enthalpy, as you know, depends upon temperature and pressure. Okay. So, to simplify the problem, again what is generally done is it is assumed that ammonia and water vapor mix without any heat of mixing. Okay, that means there is no change of phase or any chemical reaction when vapors of ammonia and water mix. Okay, in such case the enthalpy of mixer phase is given by the simple equation HV is equal to zeta V HAV plus 1 minus zeta V HWV, where zeta V, as you know, is the vapor phase mass fraction, and HAV and HWV are vapor phase enthalpies of pure ammonia and pure water vapor. Now, the problem comes because HA and HW for vapor phase are functions of both pressure and temperature. Okay. So, an approximate but practically useful method is to evaluate the vapor enthalpies of ammonia and water at pressures Pa and Pw given by Pa is equal to Y into P total and Pw is equal to 1 minus Y into P total. Remember that this is an approximate method, but it gives reasonably accurate results. And what is Y here? Y is the vapor phase mole fraction of ammonia and P total is the total pressure. If ammonia and water vapor behave as ideal gas, you will find that Y into P total is nothing but the partial pressure of ammonia in the mixer. Similarly, 1 minus Y into P total is the partial pressure of water vapor in the mixer, but you will find that most of the times the mixer deviates from ideal gas mixers. So, Y into P total and 1 minus Y into P total do not give partial pressures. Okay. Now, let us look at enthalpy composition diagram. Charts of enthalpy, temperature, mass fraction are available, which give both liquid as well as vapor enthalpy of mixers. As I said, I will show this in the next class. But right now what I will show is enthalpy composition diagram at a single pressure, because in order to understand it is easier to start with a single pressure. At a single pressure, the isotherms in two phase region are obtained by joining saturated liquid and vapor state. So, let me show the enthalpy saturation diagram, enthalpy composition diagram at single pressure. Okay. So, what we have here is the composition of ammonia in as y axis and enthalpy, I am sorry, in x axis, and enthalpy on y axis. Okay. So, again you have the bubble point line and the dew point line. In addition to that, in order to find the enthalpy of vapor and composition of vapor, an auxiliary line is shown. Okay. So, this line is an auxiliary line. Okay. And remember that this is for a single pressure, that means at a constant pressure. And the isotherms are shown in the subcooled liquid region. This is the subcooled, remember that this is subcooled liquid for this pressure. Okay. So, the isotherms are shown in the subcooled region, and this is the one typical isotherm T. Okay. So, this isotherm intersects this bubble point line at this point. Okay. So, let us assume that initially we have a saturated liquid at this point. So, it has a liquid phase mass fraction of zeta L. Okay. I would like to find out what is the mass fraction of the vapor that is in equilibrium with this solution. So, in order to find that, and what is its enthalpy. So, in order to find that, what normally is done is you draw a vertical line starting from this point and find the point that is the intersection point between the auxiliary line and this vertical line, that means this point. Okay. So, draw a vertical line and get this intersection point. From this intersection point, draw a horizontal line, where this horizontal line intersects the dew point line, that will give you the vapor phase mass fraction. Okay. So, once you get this point, the vapor phase mass fraction is obtained by going down vertically, and this is the vapor phase mass fraction, and this is the enthalpy of the vapor phase, saturated vapor. Okay. Similarly, this is the enthalpy of the saturated liquid. What it means is at this particular condition, saturated vapor of this mass fraction and this enthalpy is in equilibrium with saturated liquid of this mass fraction and this enthalpy. Okay. So, that is how you have to find out the saturated vapor enthalpies and mass fractions. And you can see that here I am varying the concentration from 0 to 1, that means from pure water to pure ammonia. So, obviously this difference, which is nothing but the enthalpy difference between saturated liquid and saturated vapor, is nothing but your latent heat of vaporization for pure water at this pressure. Similarly, at the other end, the difference, this difference or this distance gives you the latent heat of vaporization for ammonia at this particular pressure. Okay. And the line joining this point, okay, so for this pressure, the line joining the saturated liquid point with the saturated vapor point, that means this line is the isotherm. Okay. That means the isotherm T is like this. Okay. Right. And point B, what is point B? Point B is in the two phase region. So, this is the two phase region. So, if you look at point B is in two phase region, and at this point the temperatures are all equal, that means Ta is equal to Tb is equal to Ta dash. Okay. And at this two phase this is the enthalpy of the two phase mixer, I am sorry, this is the mass fraction of the two phase mixer, and this is the enthalpy of the two phase mixer. Okay. So, this is a very useful chart, and if it is if you plot this for different pressures, as you will see later, you will have different lines. Okay. Different bubble point lines, similarly different dew point lines, and the different auxiliary lines. Okay. So, you will find a whole lot of lines on a typical total enthalpy composition diagram for a binary mixer. And as I said, an auxiliary line is used to find the saturated vapor state and its enthalpy from saturated liquid state. For points lying inside the two phase region, the specific enthalpy Hb has to be obtained from the sequence, just like a two phase mixer of any fluid. Hb is equal to 1 minus the psi b into Hl plus psi b into Hv, where psi b is the quality or dryness fraction, and Hl and Hv are the saturated liquid enthalpy and saturated vapor enthalpy. Okay. And the dryness fraction is given by again what is the mass fraction at that point minus saturated liquid mass fraction divided by the saturated vapor fraction minus saturated liquid fraction. Okay. In actual enthalpy concentration diagrams, the isotherms are not shown in two phase region because for each set of pressures you have a set of isotherms in the two phase region. Okay. So, it becomes very confusing. So, normally in enthalpy composition diagrams, isotherms are not shown in the two phase region. If that is the case, how do we find the temperature in the two phase region? Okay. That I will discuss a little later, and also it is not possible to fix the state of the mixer just from temperature and mass fraction alone, because one can calculate enthalpy of the mixer from temperature and concentration, but you cannot say whether it is in superheated region or subcooled region or saturated region or two phase region just by knowing temperature and composition. Okay. For example, a liquid mixer with a mass fraction of 0.4 and a temperature of 80 degrees will have an enthalpy of 210 kilojoule per kg. Okay. This you can obtain from your enthalpy composition diagram, but it will be in subcooled condition if the pressure is 4.29 bar and saturated condition if the pressure is 8.75 bar. Okay, so depending upon the pressure for the same composition and temperature solution can be in any state. Okay, so to remove the ambiguity you have to specify the pressure so that you can completely fix the state. Okay, determination of temperature of mixer in two phase region. I was mentioning that you have to do how do we decide this. Normally a trial and error method has to be used to determine the temperature, and you have two methods, one is graphical, other one is numerical. So let me quickly explain this. Okay. So in the graphical method, let us say that point x is the point in two phase region, and I would like to find out what is the temperature of the mixer at this point. Initially what we do is we know that for this point I know that this is the mass fraction and this is the enthalpy. So I know the mass fraction and enthalpy of the two phase mixer, but I do not know its temperature. Okay. So to start with, what you do is you draw a vertical line in this manner, and the point where it intersects this auxiliary line, remember that this is auxiliary line, this is your dew point line, and this is your bubble point line. Okay. So where this vertical line intersects the auxiliary line, that is point A double dash, you draw another horizontal line. Okay. This horizontal line intersects the dew point at A dash. Okay. Now what you do is you draw a straight line passing through A dash and x. Okay. That is this line. Okay. So this line intersects the bubble point line at point A, right. So now what we have to do is you draw another vertical line from point A, and where it intersects again the auxiliary line, the point is B double dash, and from here you draw a horizontal line, and this horizontal line intersects the dew point temperature at point B dash. Okay. So again draw one straight line passing through B dash and x, and this intersects the bubble point line at x. Okay. So to repeat the process what you have to do is you have to draw again a vertical line from this intersection point, to draw another horizontal line, get this point, from this point again you draw line passing through x. So you get one more set of points. So this process has to be continued till the points here and points here converge. Normally the convergence takes place within 3-4 iterations. Okay. So this is the graphical trial and error method for finding the temperature. So how do you find the temperature from this method? Once you know the finally you know that this is, let us say that this is the line, the converged line, that means this is the line which gives the isotherm, because you know that at this point is an equilibrium mixture consisting of saturated vapor and saturated liquid. Okay. That means this one has got to be the equilibrium line, and the temperature in the subcooled region which meets this point has to be the temperature of the two phase mixer also. Okay. So you have to read this temperature. So this temperature is same as this temperature. Okay. So this is the procedure, and numerically the temperature can be obtained from the equation which needs to be satisfied for each end of the isotherm passing through x. Okay. That means the isotherm passing through the two phase mixer has to satisfy this equation. Okay. Where HV and HL, as you know, are saturated vapor and liquid enthalpies. Similarly zeta V and zeta L are saturated vapor and liquid compositions, and Hx and zeta x are the mixer properties, and we know these mixer properties. Okay. So these things are known to us. So what we do is initially you assume a guess value of HL and zeta L, then from the guess value find out HV and zeta V from your HT composition chart. Okay. Then you substitute these values in this expression, and substituting this you find this value and this value. Okay. And again use these two values to find again new values of HV and zeta V. So this procedure has to be continued till you get again converged values. Now let us quickly look at some basic steady flow processes with binary mixers. First very simple process, that is the adiabatic mixing of two streams. So let me show this process. So what we have here is an adiabatic mixing chamber, that means there is neither heat transfer to or from the mixing chamber, and in this mixing chamber two streams, one stream at condition 1 and the other stream at condition 2, they are getting mixed in this adiabatic chamber, and finally what you are getting out is a single stream at state 3. Okay. The same thing is shown on enthalpy and composition plot. So, this is the state 1, this is the stream 1 and this is the stream 2, these two streams are mixed, and let us say that this is the condition of the exit stream. Okay. So, you can point the composition, this is the composition of the stream 1, composition of stream 2, and this is the composition of stream 3. Similarly, enthalpy, this is the enthalpy of stream 1, enthalpy of stream 2 and enthalpy of stream 3. Okay. And you will find that it can be easily shown, I will show you in a minute, that this distance is nothing but m2 by m3 and this distance is nothing but m1 by m3. Okay. How do you do that? Okay. So, let me show this again on it. So I will show these equations. If you are applying mass and energy balance, then you know that from mass balance m1 plus m2 should be equal to m3. This is the total mass balance. Okay. You can also write a mass balance for ammonia, right. So, m1 zeta 1 plus m2 zeta 2 is m3 zeta 3, and this is the energy balance for the adiabatic mixing chamber. Okay. So, no heat transfer, no work transfer. So, the composition enthalpy of the mixer at the exit of the mixing chamber, for using these equation and eliminate m1, you can easily show that the mixer condition, the composition is given by this and the enthalpy is given by this simple equation. Okay. So, from that you can easily show that this mixer condition, these distances are m2 by m3 and m1 by m3. For example, as m2 increases, you will find that this point as m2 by m3 increases, this point will shift to this side. That means the exit condition will be moving closer to 2. Similarly, when m1 increases, this point will shift in this direction and the mixer condition will be 1. If m1 or m2 is 0, then you will find that this condition coincides with 1 or 2. Okay. Now, if the streams are such that the mixing condition is in the two phase region, then what do we do? For example, let us say that we have mixed two streams where stream 1 is a saturated liquid and stream 2 is a subcooled liquid. Okay. So, these two streams are mixed and you will find that the resultant mixer, that means the outlet mixer, lies in the two phase region, because as you know that the outlet condition must lie on a straight line joining point 1 and 2. Okay. So, this is the mixing process. So, the outlet condition must lie on point 3. So, when you are pointing it out on this, knowing m1 m2, and if you are finding that this point lies in the two phase region, okay, then we do not know this temperature. Okay. And two phase region means again it will have vapor and liquid phase mass fractions. Again this temperature as well as vapor and liquid phase mass fractions have got to be obtained from trial and error method, as I have explained earlier. Okay. And it can be easily shown that the fraction of vapor in the mixer at 3 in two phase region, okay, in two phase region is given by this expression. That means, this is the mass of vapor to the total mass, this is nothing but your dryness fraction, and this should be L, okay, 3L, zeta 3 minus zeta 3L by zeta 3V minus zeta 3L. Okay. So, this is nothing but your dryness fraction. Okay. So, if you know these points, then you can easily find out the dryness fraction, and geometrically you can find out once you get these lengths. Now, let us look at another process where mixing of two streams takes place with heat transfer. Okay. This is a typical process that takes place either in the absorber or generator of absorption refrigeration systems. Okay. So, let me show that process. Okay. So, this is similar to the earlier one, only difference is here you have heat transfer. Okay. So, again stream 1 is mixing with stream 2 and the resultant mixer is stream 3, and during this process some heat has been transferred Okay, if it is an absorber, you know that it is an exothermic process, so heat is transferred out of the system. If it is generator, you have to supply heat to the system. Okay, let us say that this is the process. For this process, what are the steady flow equations? Steady flow equation, just like earlier this thing, mass balance is this, total mass balance, this is the mass balance for ammonia, okay, and this is the energy balance. Okay. So, the only difference between the adiabatic mixing and mixing with heat transfer is in this term. When this Q becomes 0, you will find exactly this equation is exactly same as adiabatic mixing process. When Q is non-zero, you get this equation. So, from this equation it can be very easily shown that the exit enthalpy H3 is nothing but H1 plus M2 minus H3 into H2 minus H1 minus Q by M3. So, this is the difference. Okay. So, the same thing can be easily shown on your concentration enthalpy diagram like this. Without any mixing, this will be the process. Okay, I am sorry, without any heat transfer, this is the process. With heat transfer, you will find that the exit condition lies at a vertical distance below this point if heat transfer is from the system. Okay, and this distance is nothing but the heat transfer rate divided by the mass flow rate of the solution at condition 3. Okay. So, if you know these two things, first find out this point assuming that it is adiabatic mixing, then this point is simply assumed simply obtained by drawing a vertical line and going down by this much distance. Okay. That means this is without any heat transfer, H3 dash is the specific enthalpy and H3 is enthalpy with heat transfer from the system. Okay. If the heat transfer is to the system, obviously this point will move up. Okay. This is for the positive Q, whereas this is for the negative Q. Okay. So, with heat transfer from the mixing chamber, the exit state lies at a vertical distance of Q by M3 below or above the state which would result without heat transfer. That is what I have explained just now. Now, let us look at another simple process, that is the throttling process. As you know, throttling takes place in the solution expansion valve of the absorption refrigerant system. Okay. So, throttling is an isenthalpic expansion process, and during this process there is a possibility of vapor generation due to flashing. Okay. This we have seen earlier. If this is the case, then you will find that the exit condition lies in the two phase region. If the exit condition lies in the two phase region, again you have to use a trial and error method to find the exit temperature and vapor fraction. Okay. So, let me quickly show the throttling process. Okay. So, as you know, this is the throttle valve. So, a solution at condition 1 passes through the throttle valve and it emerges out at point 2, and if the pressure P1 is at the condition 1 and if P2 is at the exit, and you know that P1 is greater than P2. Okay. And this is typically an isenthalpic process. So, there is neither heat transfer nor work transfer during this process. So, if you are applying mass and energy balance, you will simply find that the composition remains constant and the enthalpy also remains constant. So, if you are trying to show this throttling process on enthalpy composition diagram, you will find that both inlet and exit points are on the at the same point. Okay. That means they are identical. Okay. Why they are identical? Because enthalpy is also same as this equation shows, and concentration is also same, right. So, they will be identical, but we know that at this point the pressure is different, and if there is any vapor generation, the temperature also will be different. That means pressure is will be lower than outlet pressure will be lower than inlet pressure. Similarly, outlet temperature will be lower than inlet temperature. Okay. So, how do we find these outlet and inlet pressures? We know that this exit condition, for example, point 2, it is a mixture of saturated liquid plus saturated vapor at outlet pressure P2. Okay. That means suppose this is the saturated liquid condition and this is the saturated vapor condition at the outlet pressure P2, and if you know these by trial and error method, then you can find out the temperature. Okay. Because this temperature is nothing but the temperature of this isotherm. Okay. So, this is how we have to find the exit condition of the throttling process. Now, let us look at another simple but important process, that is called heating and cooling process. So, let me first explain the arrangement. Okay. What we have here is an arrangement which consists of two heat exchangers, heat exchanger A and heat exchanger B, and also two separators, separator A and separator B. Okay. So, initially I have taken a subcooled solution. Okay, this is the subcooled solution, remember, and here pressure is constant everywhere. So, I have taken a subcooled solution at state 1 and I have heated that subcooled solution in a heat exchanger A by supplying heat 1 Q2. Okay. So, heat is supplied and this comes out at point 2. Okay. And this heat supplied is such that point 2 lies in the two phase region, that means at point 2 you have both liquid and vapor. Okay. Then what is done is this liquid and vapor two phase mixer is fed to this separator A. In the separator, the saturated liquid at state 3 is separated from saturated vapor at state 4. So, this is the saturated vapor. Okay. That means separator, what is the function of separator? Function of separator is simply to separate the liquid from the vapor, okay, at the same pressure, and there is no heat transfer or anything in the separator, that is the assumption. So, here we are separating out the saturated liquid and vapor. Then here you have saturated vapor, and what we are doing is I am cooling this saturated vapor in this heat exchanger B by extracting this much amount of heat. Okay. So, first the solution is heated in heat exchanger A and liquid and vapor are separated in separator A, and then the saturated vapor is cooled in heat exchanger B by rejecting heat to outside. Okay. And it is cooled in such a way that this condition again lies in the liquid and vapor phases. Okay. So, these heat transfer rates should be in such that at the exit of heat exchangers you have two phase region. Okay. So, again I am using another separator B where I am separating out the liquid from the vapor. So, finally, I am taking the vapor from the arrangement at this point, saturated liquid at this point and saturated liquid at this point. So, this is the arrangement. Okay. Suppose I am plotting this process on enthalpy composition diagram, how does it look? Okay. So, we have started with subcooled liquid at state 1 and we have heated this in heat exchanger A. So, this is your heat exchanger A. Okay. So, since this is a single stream, you know that the exit condition will lie simply at a vertical distance of 1 Q2 by M1 above this point. Okay. So, I can easily find out this enthalpy, and during this process your concentration remains same. Okay. So, zeta 1 is equal to zeta 2 during this process, right, but the point 2 lies in the saturated lies in the two phase region. Okay. This is the liquid plus vapor region. So, that means at this point you have saturated liquid at point 3 and saturated vapor at point 4. Now, if you look at the earlier diagram, what we have done is at this point we have taken out the saturated liquid and saturated vapor from the separator A. Okay. So, this is the process occurring in separator A, and from that point onwards what is done is this saturated vapor, okay, at condition 4 is cooled in the heat exchanger B. Okay. So, this is the process in heat exchanger B. Since this is cooled sensibly, I mean this is cooled by rejecting heat to the surroundings, you find that the exit condition lies at a vertical distance of 4 Q5 by M4 below this point. Okay. So, you can again easily find out this one if you know this and if you know this. Okay. Similar to this, if you know this you can find out this point. So, we have got the point 5. At this point again this is in two phase region. So, again you have a mixture of saturated liquid at 0.6 and saturated vapor at 0.7. Okay. And at this point the vapor is taken out. Okay. So, what is that we have done during this process? What we have done during this process is we have taken subcooled liquid. Okay, we have taken subcooled liquid at this point and we are getting a vapor, okay, that is rich in ammonia. Okay. Suppose this process is continued further. Okay, you will find that as you are you have taken again this vapor and this vapor is again cooled. Okay. And you have separated out again the liquid and vapor. So, you can see that this point, that means the outlet point, progressively moves closer to the pure ammonia state. That means you are getting vapor that is rich in ammonia at the exit of this arrangement. Okay. That means the whole system is working like a rectification column. So, that means I have used a combination of two heat exchangers and two separators, and I started the process with a subcooled liquid. I have heated the liquid then I separated the saturated liquid and vapors, then I cooled the saturated vapor, again I separated the liquid and vapor fractions, and finally I have a rich ammonia vapor. Okay, rich vapor strong I am sorry vapor that is rich in ammonia. Okay. So, this is actually the purpose of any rectification system where you feed the liquid and you get pure components, right. Now, if you apply the simple mass and energy balance for these components, for example, for the heat exchanger, as I explained, total mass is conserved, concentration remains same. So, this is the energy balance. Okay. This is the heat supplied is utilized for increasing the enthalpy, okay, and this is the mass flow rate. Okay. And similarly, mass and energy balance for the separator. In the separator, this is the total mass balance, that means whatever mass is coming in is mass going out in liquid form and in vapor form. Similarly, you can write mass balance for ammonia. Okay. So, this is the amount of ammonia entering into the separator A, and this is amount of ammonia leaving the separator A, okay, in liquid form, again in vapor form, and this is the energy balance for the separator, no heat transfer or work transfer. So, this is simple energy balance for the separator. Okay. So, similarly, a set of equations can be written for heat exchanger B and separator B also. Okay. For these two also you can write similar set of equations. From these equations you can show that M3 by M2 is nothing but zeta 4 minus zeta 2 divided by zeta 4 minus zeta 3, okay, length 4 2. This is nothing but your mass fraction, liquid phase mass fraction. Similarly, this is the vapor phase I mean liquid this is the ratio of mass of saturated liquid to the total mass in separator A, and similarly this is the ratio of saturated vapor to the total mass in separator B, okay, and ultimately they can be expressed in terms of the different lengths, okay, which are shown in the earlier diagram. So, if you can draw the diagram, you can easily find out how much liquid you have, how much vapor you have, and as I said, you can write similar equations for heat exchanger B and separator B. Okay. So, as I said, from the arrangement consisting of heating, cooling and separation, one finally obtains vapor that is rich in ammonia. Okay. So, this process is similar to rectification. So, in this case heat exchanger A plays the role of generator, while heat exchanger B plays the role of a component called deflegmator. Okay. However, in actual systems just a generator and deflegmator are not sufficient. So, we also use a rectification column which is introduced in between generator and deflegmator. This is required to improve the process of rectification. Okay. So, an actual absorption refrigeration system based on ammonia water will have the generator, a rectification column and a deflegmator. Okay. And the principle is what I explained just now. Okay. So, I will explain the basic system consisting of all these components and the working principle in the next class. So, let me quickly summarize what we have learned in this lesson. So, in this lesson systems based on ammonia water are introduced, and properties of ammonia water are discussed with reference to composition in liquid and vapor phases, vapor pressure and enthalpy data, and some simple processes using mixers are analyzed assuming steady flow process. Okay. In the next class I shall discuss the actual systems. Okay. Thank you.